All right, good morning.
Good morning.
Let's see what we got here. All right, hopefully that is sharing my screen.
Yeah, we can see it.
Awesome.
Document cam.
All right, so I want to talk a little more about GDB today because we kind of ran out of time at the end of Tuesday's class. And then I want to talk about the ODP that was due yesterday, and then I want to talk about the current ODP, which is due on Friday. And then we're going to switch gears and go back to talking more about Linux things and looking at more aspects and commands in Linux and working up to writing shell scripts in Linux. So anything that anybody wants to go over before we get into all of that, we can start with whatever.
Maybe this will be covered when you talk about GDB, but I was wondering, how do I verify that something is doing that I want it to do? Like, for instance, in my read keywords function, how can I test if it's actually opening the keywords text file and storing the words like I want it to be doing?
So you want to get in the habit of writing test files, preferably as you're developing these functions, be writing programs to also test them. And so, for example, read keywords. Let me pull up the programming assignment so I don't do this from memory. So let's see, 224 fall homework PA2. So read keywords takes a file name and an array of keywords. So you could write a main program and make yourself a keyword file, a keyword array. And then you could do something like, integer num equals read keywords. Put in the name of your file. And it doesn't have to be keywords.txt for a test program. It could be anything you want, comma, and then the name of the array. And then make a print statement to print out num. And if you've got 5 words in this text file, num should be equal to 5. So that's one thing to test, is make sure read keywords is returning the number of things that it read from the file. And then you could make a for loop for I equals 0 to num minus 1 and just print each element of that keyword array. So, use a %s. And if you print out keyword bracket 0, that should be the first word that was read from the file. Keyword bracket 1 should be the second word that was read from the file, and so on. Does that make sense?
Yeah, and I would just be manually typing in the keywords in that main function.
So this would be making a file called keywords.txt. And when you run this program, if this is your whole program, there's nothing to type. Right? This function will open the file, read in the words, save them in this array, and then this loop will print the contents of that array.
Okay, so as long as I have a keywords text file in that directory as well, is what you're saying?
Mm-hmm.
Okay,
Yeah.
got it.
And if you don't, then when you run this and you print out the number, it should print -1, and then this for loop will never do anything. So that should still work, but it'll tell you that num is -1, which tells you, hey, it didn't open the file.
Okay. Okay, got it.
Okay.
And I wouldn't be able to do this like directly from my read keywords function, like just basically copy this kind of a deal into that function.
You could put this in the beginning of read keywords, right, and make a call to it, and you know, that would turn your read keywords.c file into a main program, and so you'd need to remove that. Or, you know, you could put print statements inside this function to print out things as they're being stored in the array and so on. So if you're developing this function, you probably want to be putting, you know, debug print statements inside the function itself. But when you're done and you think your read keywords function is finished and you want to check it, call it from another place, like a main program, right? And that's kind of the acid test.
Okay, thank you.
And so, yeah, someone asked in chat, how do you make a PA2 subdirectory visible to Git? And someone answered, just push a file from within that subdirectory. So if you have an index.c file, you can say git add index.c, git commit, and then git push origin master. Absolutely do not do a git init though. If you do git init, it will kind of wreck your repository. So just do git add, git commit, and git push.
Just so would we push things to Git? Do you just want us to push the .c files for PA2, or does it matter if we have .o files in there? Because I accidentally committed all my files.
Yeah, it's totally fine either way. It's probably easiest to just say git add star, and that gets you everything, because occasionally people will do just the .c files and they'll forget to do the .h file, or they'll forget to do the make file, or things like that. And if you git add star, you know, none of these files are terribly big, so it's not taking up a lot of space. And when I download, I get your .o files, but I'm just gonna overwrite them when I recompile, so that's fine. And yeah, so someone else said in chat, usually you don't put the .o files because there's no need, because you're putting the source code in there. And so you can recompile those .os, you can recompile the executable. So if this was something that you were putting out, you know, on GitLab for other people to download, you would probably just want the .c files. So there's less to download and it'll recompile and so on. And so you can either don't push them or make a git ignore file, a .git ignore, and have it automatically ignore, you know, like .o files and so on. But for PA2 and if we're new to using Git right now, easiest thing, just git add star, and it'll just add everything in your directory.
Okay, thank you.
Yeah, you're welcome. So yeah, let's see. Let's start with the ODPs, and then we'll go ahead and we'll talk about GDB. So So 416 was this function that removes all occurrences of the letter X from a string. And it's a function. It doesn't do any, fgets or any printfs or anything like that. It's a function that takes an input string, removes the X's from it, and saves that in an output string. And it can be something like this, right? So same thing that we did with the mix function. We're building an output string one character at a time. And so in this case, I have my output array. That's the second argument. And I have a variable that keeps track of where we are in that output string. So I said output location equal to 0. This is our standard for loop that loops over all of the characters in the input. And the whole mechanism here is if the input character is not an X, copy that input character to the output string and increment that output location. And that's really all you got to do. But you have to make sure you put a null terminator on the end. So if we do our usual loop where we say iloc equals 0, iloc less than string length, that will work on all the actual characters in the input string, but we'll still have an unterminated output string. And so at the very end, we would need to say out bracket outloc equals \0. So something like this. And our output is called oloc. Right? And if oloc is always the location where the next character is going to get written, this will store a null terminator in that location. But you can get a little tricky. And so in this for loop, I'm looping up to and including string length of n. And so there's this business, since we start counting indices from 0, if we have a string like ABC, its string length is 3 because it's got 3 characters, ABC. So here's ABC. String length equals 3. And if this is going to be a null terminated string, it's ABC followed by a null terminator. Where does that null terminator get stored? It gets stored at index 3. So string length always tells us where the null terminator is. And so in this code, I was looping up to and including string length. So the last time through this loop, iloc is actually pointing to the null terminator. The null terminator is not an X, and so this is going to copy the null terminator into the output string, and so we don't need to do that separate assignment after the loop. So that's just a different way of building a string and terminating it at the end. So there's different ways to do this, but that's the basic setup for this remove function. And then for 417, we have almost exactly the same behavior, but one modification. We only want to remove the first occurrence of a lowercase x, and then we want to start keeping all the other x's. So if your input is something like hexaflexa, your output should be heaflexa. So we remove that first x, but we keep the second x, and we keep the third x, and so on and so forth. And we can do that with a flag, right? So, have an integer called sawx, which starts off at 0, set to 1 once you see an x. And then for each character in your input, if you already saw an X, just copy the input character to your output string. So do this thing. Do this string regardless of whether the character is an X or not. That's if you've already seen an X. Otherwise, if you haven't seen an X yet and the current character is not an X, still copy it to the output. Otherwise, you're seeing your first X. And so just set saw X equal to 1, but don't copy. And so you make this one change to your loop from remove, which uses a flag. Initialize it to 0 to say I haven't seen an X yet. And if we've seen an X, we're just going to copy regardless of what the character is. If we haven't seen an X and our character is not an X, we're going to copy it. But if we haven't seen an X and we're seeing an X, we're not going to copy because we're skipping that first X, but we set this flag so that in the future we can say, hey, we already saw an X. Let's copy even if we have another X. And so this is this stateful programming that we talk about sometimes. Does that make sense? Cool.
You're basically, sorry, I might have missed some of that because I had to get up for a second, but
No problem.
it like towards the end of there where the equals 1, are you basically using a flag? Is that right?
Exactly. That's just a flag.
Okay.
So saw X is a 0. There's an H. It's not an X. We copy it. There's an E. It's not an X. We copy it. There's an X, right? It's not different from an X, right? Saw X is not 1. So this is the first X. So we set saw X equal to 1 now, and we don't copy. So we copy the H and the E. We skip the X. Now here's an A. Saw X is 1. We copy. There's an F, L. When we get to this X, saw X is a 1. We're just going to go ahead and copy it.
Okay.
And, you know, from this point forward, this is what happens every time through the loop. We just copy input to output. So yeah, that's just a flag.
Okay. Cool. I might talk to you about that because I tried that like when I was initially doing 417 and I just couldn't get it to work. So I'm curious to see how that would work.
Okay.
Cool.
Let me take a quick look at your code. Hold on.
I went with something like completely different, but I was just curious. I've noticed like I've been having like issues, like I know exactly how I want to solve a problem. And like I think you saw it when with my stick game. I don't think I exactly translate what I'm trying to do to code. I think like small things or like
Okay.
things in the wrong place. So I don't know. I'll just drop by your office hours or something.
Okay. But this is a really good comment though, right? Or a good opportunity to make a comment, which is if you write code that you believe should work, it's really good practice to do whatever you can to make that code work, right? And it's tempting sometimes to say, well, I must have the wrong idea, and rip that up and try something different. And when you try something different, you know, then maybe that works better. But you should always try to dig into, you know, the thing that you thought would work and didn't. Try to figure out what happened there. Because that's that critical learning opportunity. That's that, you know, gift of the bug that will reveal something that will be very valuable to you down the road. So you know, if you're racing the clock and you just need to get it done, maybe it's better to just try something different. But at some point, it's really valuable to go back and actually like dig into those things that don't work. Those are the best learning opportunities.
I had a random question about a bug that I had in the stick game.
Mm-hmm.
When I was trying to check whether it was equal to 1 or 2 or 3, for some reason, when I would use does not equal 1 or 2 or 3, that did not work. And I thought that it would. But if I did is not between 2 or 3 or between 1 and 3, that worked. And I could not figure out why.
Is that still in your code or did you change it?
I changed it, but it had
So,
been. Yeah, go
so
ahead.
can you type that in the chat window, maybe the way that you were trying to do it?
Sure, let me pull it up. I'll check it out on GitLab and then type it in.
Okay.
I'll
So if you do something like I is not equal to 1 and I is not equal to 2 and I is not equal to 3, that should work pretty well. But if you try to do something like I is not equal to 1 or 2 or 3, that's not going to work.
Yeah, so I did does not equal, and then I did like exact, like does not equal 1, does not equal 2, does not equal 3. The way I pasted it
this?
ended up working. Yeah, something like that.
Okay. Yeah, this should work.
Maybe I just forgot the parentheses around the I does not equal 3 kind of a thing.
And I
Does that
don't know
matter?
if those are strictly necessary or not, but rather than learn the rules for that, I just always throw in parentheses. And sometimes people will use ors here instead of ands, and that will end up not working. So
Yeah, I definitely did ands.
And so this is the condition for an error. The condition for a non-error would be I equals 1 or I equals 2 or I equals 3. That's no error. So this is actually the opposite of that. And that's good old De Morgan's theorem, right? The negation of this is negation of each of these, and the ors get changed into ands. And so sometimes something goes wrong and people put ors in here, or they put ands in here, or they do something that's just totally not the same syntax like this.
Yeah, maybe that was the problem. Maybe I was doing it the middle way. I thought I had done it the top way, but looking back at it, it looks like I tried to do the does not equal 1 or 2 or 3 like that. That makes sense.
Yeah, so I think this, I don't know what this will do exactly. I think it will see if I is different from 1. And regardless of that, then it will say or 2, and 2 is considered true. So this is true and this is true. And so I think this will always evaluate to true regardless of, yeah, so someone in chat's ahead of me. This will always evaluate to true regardless of I. But it's one of those things that C will not tell you about, right? It's totally happy with that. It's like, cool, I can do this. And it doesn't even give you a warning probably.
Yeah,
So
I was stuck on that for a while.
One thing people sort of complain about with C sometimes is it really does do, you know, whatever you tell it to do. That's a feature or a bug, depending on your perspective.
Correct me if I'm wrong, but I'm interpreting the top one here. I like if the answer was, or if I was 3, for example,
Mm-hmm.
would it like, this would always be false, almost no matter what you gave it? No, hold on. Because I does not equal 1 first, and if that's true, that would be 1. And I does not equal 2. Okay, so, oh man, would it be?
Yeah. So suppose I equals 1, right? This fails to be true. And so the whole statement is false. So if I equals 1, there's no error.
I think the thing that's confusing here is and instead of or. And means it okay, you know what it means. It just is, it can mess up your brain when you try to think of ands and ors
Right.
too quickly.
So one way to do this is to plug in truth values, right? So suppose I is equal to 2. Okay, so I is not equal to 1, that's true. I is not equal to 2, that's false. I is not equal to 3, that's true. So this is true and false and true. And this turns out to be false, right? Because true and false and true, those aren't all true. But if I was equal to 4, right? I is not equal to 1, that's true. I is not equal to 2, that's also true. I is not equal to 3, that's true. So the value of this is true and true and true. And that's true. So this is an error condition. And so, yeah, those are confusing at times, and at other times they make sense. And eventually they get confusing less and less of the time, but they still get confusing to everybody at some time. And like I say, we can always defer to De Morgan by, you know, what's the condition when the input is correct? Well, I has to be 1, or I has to be 2, or I has to be 3. And then if we want the error condition, we negate this. So in the language of CSE215, right, this is what we're after. And De Morgan's theorem tells us this is the negation of this, ANDed with the negation of this, ANDed with the negation of this. Well, the negation of I equals 1 is I not equal to 1. The negation of I equals 2 is I not equal to 2, and so on. And so depending on whether we natively think in terms of, you know, positives or negatives, sometimes it's easier to write down the opposite condition and then negate it. Or if we wanted an error condition, we could say if not I equals 1, or I equals 2, or I equals 3. And that's an error. So that's the condition where the input's legal, and throw an exclamation mark in front.
So you can just factor things out like that.
Yeah, yeah.
Oh, that's cool.
Yeah, and sometimes that's the clearest way to do it. All right, cool, good stuff. Other questions?
So I actually have another question back to the ODP thing. Sorry.
Yeah.
So, and my question kind of comes down to string copy.
Okay.
I won't say exactly what I did, but I've noticed string copy, like if we put a parameter on something like, you know, hey, I'm looking for a space, and as soon as you find a space, string copy will just copy everything from that point. Is that correct?
So string copy is pretty unsophisticated. It just takes 2 null terminated strings, and it copies this entire string into that entire string.
Right. So
And
like,
so
oh, sorry.
if you're trying to use that to break up a string, you have to start playing around with using indices and ampersands on here, or injecting null terminators into here, or something like that. And
Yeah.
it's doable, but it's not particularly well suited to it. But if you're thinking about PA2 here, your best bet is really read your input 1 character at a time instead of a line at a time.
Yeah. Yeah. So I was just thinking in terms of like, you know, like let's say we iterated through a character and we put like a parameter on that iteration of like, like let's say we're iterating through an array of just like numbers like 1, 2, 3, 4, 5, 6.
Mhm.
And so, we're iterating through and we're saying that if whatever that array, when that equals 6, and then, we break that loop, and then outside of that loop, we do this string copy thing, would string copy would just copy everything from 6, so it would only copy 7, 8, 9, 10. In like that instance, I sorry, I don't think I'm wording this question very well.
So if you said, ampersand source bracket 6, that would copy from the 7th character of this string into destination.
Okay.
But that can get a little confusing at times.
Yeah.
But yeah, that would work.
Okay, cool.
String copy does nothing magical at all. String copy is basically, for I equals 0, I less than string len, or less than or equals string length source, I plus plus, dest bracket I equals source bracket I. That's really all string copy does.
Oh, okay.
Right, it just copies character by character up to and including the null terminator and source.
Okay, so if we do get something to work with string copy, because I know like on the below thing, we were having to add the null terminator, string copy, we'll just bring that with it. That's correct.
String copy, as long as source is null terminated, will terminate destination as well.
Okay, cool. Thank you.
Okay, cool. All right, so let's play with GDB a little bit more. So I have some test code in here. I have an attempt at a mix function for the old ODP, and I have a main program which is designed to test this mix function, and so it mixes ABC in 1, 2, 3. And so I can compile these together and run main. And as we noted on Tuesday, this mix function does not seem to work. Right? I should get, ABC 1, 2, 3 should give me A1, B2, C3. And instead it's giving me AB2. So we can use the debugger to try to figure out what's going on. So when I compile, I'm going to put a -G switch in the beginning, which says link with debugging. So GCC-G. This says include GDB support. And then to actually debug my program, instead of saying main, I'm going to say GDB space main. And that's going to run my code inside the debugger. So GDB main says run the debugger. So I'll just put comments over here on the right. And once we're in the debugger, we can do a number of things, but usually the first thing we're going to do is the command start. And that begins the debugging process. And I can use commands like list, for example, to look at the code in my file. And when I said start, it said temporary breakpoint in main.c line 5, starting the program main, temporary breakpoint main.c line 5, and line 5, it says looks like a curly bracket. So if I say list, I can see my program main.c. And yeah, the first sort of executable line of code is really line 5. That's where my main program begins. This just defines a bunch of function prototypes and so on. This is a function prototype. This is a space. This begins the declaration of the function main. But this is kind of the line where the function actually begins. All right, and then we said there's two ways we can move forward. We can say next, or we can say step. And next is called a step over, and step is called a step into. So if we want to debug a function, we're going to say step, and our debugger will move into that function. If we say next, it will run an entire function and then come back to us and let us do other things. So let's just go ahead and say next, and I can abbreviate commands. N is a good abbreviation for next. And so it's about to call this function mix. And I can also look at values of variables. So I can say print and some expression. And so I can say print out. And it'll show me my current value of this character array out. Now I declared out up here to be 120 characters. It happens to contain 34 null terminators, followed by ASCII code 377 in octal, 29 null terminators, this peculiar pattern, another 21 null terminators, this peculiar pattern, and that's the end of the array. So this is random stuff. And if I run this again, and I look it out, in this case, it looks like it contains the same stuff as before. But that's kind of random. Sorry, say again?
Oh, it unmuted me. I'm sorry. I was talking to my mom.
Okay. All right. So let's go ahead and debug our function mix. So I want to say step. And when I say step, it tells me, hey, you are about to execute this statement inside this function called mix. And it's showing me that mix was called, and the first argument is S1, and the value of S1 is this. And it's a string containing ABC. And the value of S2 is this, and that's a string containing 1, 2, 3. And the value of out is this, and that's a string containing nothing. And we're at line 7 in mix.c, and if I say list, I can see the source code, first few lines of the source code for the mix function. So any idea what this number 4000748 is?
I don't know why, but the 0x makes me think a memory address.
That's a memory address, exactly. And we can examine that memory address by saying X followed by that number, and it'll show us what's stored in memory at that location. So the first thing stored is the byte with hex value 41, followed by a 42, a 43, and a 0. Well, this is the ASCII code for A, this is the ASCII code for B, this is C, and this is a null terminator. So this is quite literally what the string ABC looks like in memory. All right, well, it says S2 equals 4000744. So we can look at that location in memory. And that contains a 31, 32, 33, and 0 ASCII codes for the digits 1, 2, 3, followed by a null terminator. So that's the actual contents of the machine's memory where the string 1, 2, 3 is stored. And if we look at this address, yeah, go ahead.
I'm noticing you're reading it backwards.
Yeah.
For that particular reason.
So this is potentially peculiar, but if I say examine byte 4000744, it shows me at that address in memory there's a 31. And at the next location 745 there's a 32, and at the next location there's a 33, and at the next location there's a 0. So if I just say X, it's going to show me 4 bytes at once. And what order will it put those 4 bytes in? Will it put the first byte on the right or on the left? That's not well defined. on this system with this CPU, with this debugger, it's putting that first occurring byte on the right, and it's putting the last of the 4 bytes on the left. But on some systems, you might see these in the other order. You might see a 31, a 32, a 33, and then a 0 at the end. And that's related to something called the endian of the system. And there's systems that use big endian, and there's systems that use little endian. And whether a system is big endian or little endian relates to when you have 4 bytes and you're displaying them like this, where is the first byte? Is it on this end or is it on that end? And it's not standardized. So for us,
Oh,
we can
lovely.
examine, say again?
Said, oh, lovely.
Yeah, it is lovely, because when machines start talking to each other, if I'm storing my stuff one way and you're storing stuff a different way, we can't talk easily. I'm going to send you the number 1, and you're going to see this as the number, you know, of something in the tens of millions. And so when we do networking, there's a standardized network order that pins down which way things should be stored if you're passing things like, you know, port numbers or information like that over the net. And each machine has functions built in that will convert from whatever version the system is using into the standardized network order. So yeah, I think this is a Gulliver's Travel, partially reference. But it also refers to whether things are stored on the big end or the little end of the number. The big end is on the left, the little end is on the right. So I don't know if the play on Gulliver's Travels is intentional or after the fact, but my architecture teacher referred to that. So all right, so we can go back to examining an entire word at a time by saying x/w. All right, so these are the strings being operated on, and if we examine this location in memory, well, we know there's going to be a bunch of nulls, right? The system told us there were 34 nulls in the beginning, and then there's some stuff that's not null. There's an FF. Well, that was that octal 377, and so on. So we'll get a lot of practice this term, and especially in winter term, looking at things in memory with a debugger. And this will be critical in CSE224, because we're going to be basically manipulating memory kind of with our bare hands. And so we'll use the debugger to see what's going on. For now, just debugging this mix function, we don't have to get down to this level. We can sort of stay at the level of C code. And so let's execute our loop. So I'm going to say next. And it's going to start a for loop. And if I just hit enter in GDB, it'll repeat my previous command. So enter will say, go ahead and do next. And it's about to say outloc bracket outloc equals S1 bracket inloc. Okay, so what's in location? That's 0. What's out location? That's 0. What's S1 bracket inloc? That's the letter A. What's the current value of out bracket outloc? It's a 0. Okay, so it showed me the statement. That's the statement that will be executed next. So let's say next to execute that. And now if I print out bracket outloc, hey, it's got an A in it. So far our code's doing what it's supposed to do, right? It was supposed to copy the first character of S1 into our output. This is where having comments on your code would be really useful, because I'm looking at my code one line at a time in the debugger. It would be nice to have a comment here like, you know, take next character from first argument and copy to end of the output variable or something like that. Okay, we're going to increment output location, so we'll execute that. So now outloc is equal to 1. And now we're going to copy S2 inloc to outloc. So I'll look at S2 inloc, that's the digit 1. So let's go ahead and do that copy. And now if I look at output location, look at out, it's a letter A followed by a digit 1. So our first pass through our loop created the A, created the 1. So far, so good, because each pass through the loop should mix another pair of characters from the input. So we're back at the top of our loop. We'll go ahead and we'll say we're about to do this copy. So I can print S1 bracket in loc, and that's the letter B. And let's go ahead and execute that copy. And now take a look at our output. And suddenly we see something went wrong. Because our output should be an A followed by a 1 followed by a B, but instead it's an A followed by a B. That 1 has disappeared. Well, what went wrong with this statement? Let's take a look at what outloc is. Outloc equal to 1. So this statement did exactly what we told it to do. It copied that B, the second character of S1, into index position 1. The problem is index position 1 is not where we wanted to place the B. We wanted to place the B at index position 2. But when we ran our code, we can see it's placing it in index position 1 because that's what outloc is. So what's wrong with my mix function? Why did it put that second character into the wrong position in the output?
Because you're not incrementing outloc again.
Because I'm not incrementing outloc again. And so if your code is well understood by you, if your code is documented and commented, if you have pseudocode and you know exactly what your code should be doing, it almost leaps out and jumps in your face and waves its hands at you and says, hi, look at me, right? I wanted to copy a B into index location 2, and the debugger tells me clearly I just copied it into index location 1. Outloc has the wrong value. And so you're kind of forced to say, you know, why is outloc not a 2? Why is it only a 1? Because I didn't increment it from a 1 to a 2. So I've got a bug. I forgot to say outloc equals outloc plus 1. So Control D to exit the debugger. It'll say, you know, this is going to end your session. Type a yes to say that's fine and fix your code. So add that increment over there and repeat the process. So recompile with a G switch, rerun with GDB. Now, if you want, you know, you can run your program now and see if it's doing the right thing. And it's doing something. It got output was A1, B2, but there's a half triangle question mark sitting here at the end. That's certainly not correct. So let's run the debugger. Let's start it. Let's say next, let's do step to go into the mix function. And let's start stepping through. Now, how quickly you do this depends on how comfortable you are with debugging, how confident you are with different parts of your code. I'm just going to step through those 4 statements, and I'm going to look at what out is right now. And it's an A and a 1. That seems pretty good. I'm going to loop through here again, and I'm going to look at out. And it's an A1, B2. That looks pretty good. I'm going to loop through here again, and it's not looping a 3rd time. It exited my for loop after doing A1, B2. And what I wanted was I wanted it to do 3 sets of characters, A1, B2, and C3, but it only did 2 sets of characters, A1, B2. It looped 1 time too few. So what's going on in my code? And I can say list mix to look at that function. So anybody see the issue here? Why didn't it loop enough times?
You're doing 1 less because you have string length -1.
Yeah, I have a string length -1. So do your test case. If your string is ABC, string length is 3, that's how many times I want to iterate. And if I do string length -2, I'm only iterating twice. -1, I'm only iterating twice. So I either have to do from 0 to inloc less than string length, or I could do 0 less than or equal to string length -1. So leave your debugger, go back into VI. Let's just get rid of the -1. Let's save that, recompile. Let's run our program. ABC 1, 2, 3, they get mixed correctly. That looks great. If I go back in time and I assess this, I'm not going to get 10 out of 10 on every test. And so you need more test cases. And when you're playing with strings, a really good test case is to run your function multiple times within one program. Because remember, when I looked at this in GDB, my initial value of out was a bunch of null terminators. But we don't know that that's always going to be the case. So let's do a few different things. Let's try this. And then let's do one more case. Let's just do an X and an O. And let's mix those together. So I'll compile all that. I've got the G switch. It doesn't matter if I don't use it, right? If I want to run GDB, I've already linked in the debugging symbols, but I can still just say main to execute my program. And I can see something's definitely wrong here. Because hello 1, 2, 3, 4, 5, that seemed to mix together fine. ABC 1, 2, 3, well, that mixed, but I got extra stuff at the end. And XO mixed, but I got extra stuff at the end. And hey, this extra stuff at the end isn't just random. It looks like stuff that was in there to begin with. So let's GDB, let's start. Let's just go ahead and run through mix with hello 1, 2, 3, 4, 5, because we know that works. And if we print out, there's what out looks like. And so now let's step through our print statement and let's step into our mix function and let's start executing this loop. So this is going to loop 3 times. So let's go ahead and loop. That's the first time. That's the second time. This is the third time. And so if I look at out right now, it should have ABC 1, 2, 3 mixed together. That's right. We come out of our for loop and it's going to return, right? Line 14 is the end of my mix function. And what's my output string look like? A1, B2, C3, L4, O5. So what's going wrong here? I'm trying to mix ABC 1, 2, 3, and this is the string that it's returning.
It's just overwriting the old string. It's not.
Yeah. It's overwriting the old string. So I've correctly written the first 6 characters, A1, B2, C3, but my string actually has this extra stuff after it. How do I make that stuff go away?
Okay, so that it adds a null character at the end of the mix function.
Add a null terminator in there. Or as someone else said in chat, I didn't initialize to a bunch of nulls at the beginning. So anytime that we build a string in C, it's our responsibility to put a null terminator at the end of the string. And if we don't do that, and then we try to print the string, the print function is just going to say, you know, well, none of this is null, none of this is null, none of this is null. It's going to consider all of that to be part of the string. So we need to add a null terminator. So go out of the debugger, go back into your function, and So add a null terminator to the end. And the trick we've talked about in class is, you know, if we're using outlook to always mean where the next character should get stored, we can just say out bracket outlook equals null terminator. Compile that, run it. Now it's rock solid. 5 characters mixed together, fine. 3 characters, 2 characters, seems to be doing the right thing. Maybe I'd go back and put this extra test at the end, and then maybe run one more really goofy test, which is to mix 2 strings containing nothing. And that should give me back an empty string. So compile that, run that. That looks really good now. So now I could take this and I could assess it, and this should give 10 out of 10 on every test. And if it doesn't, then there's some other weird test case that I haven't thought about, some situation that's treated differently because it's, you know, got something weird about it. So that's an example of using GDB to help with this whole digging into bug process. And GDB, you know, it doesn't actually tell you what your bug is, but it lets you see what the computer is doing as your code executes. And this goes along with a concept that I call playing computer. And playing computer is kind of like doing this thing, right? If you've got an if statement and it doesn't seem to be working correctly, pretend you're a computer and evaluate this, right? So let's just say I is equal to 4. So the first thing I'm going to do is evaluate this. I'm going to get true or false, and then I'm going to evaluate that, and then that, and then I'm going to try to AND them together. And we can pretend we're a computer when we study our code and try to see what it's going to do. So for example, if I'm executing this code, right, I can say something like, you know, suppose I'm mixing ABC 1, 2, 3 and out. All right, so I come into this function call. So I'm going to write down S1 equals ABC followed by a null terminator followed by who knows what. And S2 is going to be 1, 2, 3 followed by a null terminator followed by who knows what. And out is just going to be a bunch of unknowns. And then outlook equals 0. That's the statement right here. And now we're going to do a for loop. And the for loop begins with inloc equals 0. And string length of S1 is going to be 1, 2, 3 characters till the null terminator. And 0 is less than 3, so I'm going to go into the body of my for loop. And I'm going to say out bracket outlook, which is 0, equals S1 bracket inloc, which is 0. So S1 bracket 0 is A, so this is going to become an A. And the rest of this string, you know, we got no idea what's in there. And then I'm going to increment outlook. And I'm going to say out bracket outlook equals S2 bracket inloc. So out bracket 1 equals S2 bracket 0. There's S2 bracket 0. Here's out bracket 1. Gets written right there. And then we increment outlook. And then we go back to the top of our for loop, which means we increment inloc to a 1. We compare that to string length of S1. Well, S1 still has a string length of 3, and so on, right? So this is forgetting about what you want your code to do. This is looking at your code and writing down what it actually will do when it executes. And if you do this faithfully, you will find whatever bugs you have in your code. But you've got to make sure, you know, that, for example, you start off with making clear that you don't know what's stored after that null terminator. You don't know what's stored anywhere in out. And if you follow through your code, you will eventually find a place where what is happening in your program is different from what you wanted to have happen. And that tells you you've encountered your bug. But the problem with this is the same problem with proofreading an essay, right? You write an essay for English class and you're told to proofread it. So you read through the whole thing and it looks perfect. And you send it in and you get it back and there's spelling errors and there's grammatical errors and all sorts of stuff. Because when you proofread an essay, especially if you've spent 10 hours writing that essay, you're not actually reading it. You're recalling it from your own memory. And when we look at a program and we try to work through in our head, what is this program going to do? We don't see individual statements. We see, oh, okay, this is going to copy the next character into the next character. And so the debugger helps keep you honest, right? And so if you have a really, really bad bug to find, what you want to do is, be able to go through and play computer, pretend you're the machine, but use GDB to keep you honest. GDB will show you, what is out actually equal to after you do this statement. And if you forgot to do outlook equals outlook plus 1, you might be playing computer and you might see this and in your mind, you might just say, okay, take the next character and add it to the next location and out. And you start doing that. But if you're not incrementing outlook plus 1, that's not what this statement says. So if you're looking at this in the debugger and outlook is not the right value, the debugger will do exactly what this says. And you'll say, wait a minute, I should have gotten, A1B, but I actually got AB. And so you go back and you play computer again around that point, and eventually you find the fact that, oh, outlook was still equal to 1. And then when I did this copy, it copied that letter B into location 1. That's the problem right there. So this is part of developing debugging skills. All right, so on Canvas, let's see if it logged me out. Hey, I'm still logged in, good. So on Canvas, there's this short Gdb summary. And it's really just a handful of instructions. So use the -G switch when you compile to put in debugging symbols. Gdb starts the program, start begins execution. And then some of the commands we use: list, print, step, next, X for examining, P for printing the value of an expression. The one other thing that can be useful that I want to mention is using breakpoints. And so let's say I'm debugging, and I know that I want to see what happens inside the mix function. I can say break mix. Well, I can say start and break mix. Then I can say continue, and the program will run until it hits this breakpoint, which is the beginning of the mix function. And so now I'm at this function call to mix, and I'm mixing hello and 1, 2, 3, 4, 5. And if I want to get on to the next call to mix, I can just say continue again, and it'll run all my code in the function. It'll return, it'll go through main until it gets to the next call to mix. And now it's going to mix ABC 1, 2, 3. And maybe that's the part that I want to actually debug. So now I can start stepping through this one line at a time and so on. So you can set these breakpoints, and you can set them at particular lines of code or at functions and so on and so forth. So maybe I just want to break at the point where I'm adding the null terminator. So I can say break 15, and I can say continue. And now it will have gone through my whole for loop, mixed everything together. I'm at the point where the null terminator is being added. So I can look at out, and that's what out looks like. And I can look at out location, and that's a 6. And if I count off, that 6 is right where the letter L is. And so this is about to put a null terminator in place of the L. That feels like what I want to have happen. So let's execute that. And then let's look at out again. And hey, it worked. It made a null terminator after the 3. This looks good. So breakpoints are a way to get to interesting parts of your program without having to step one line at a time. They let you jump ahead until you hit a breakpoint. And you can have multiple breakpoints. And if you've done Engineering 270, you know about breakpoints because we use them in the debugger there all the time. So those are the main commands that will get you through almost all of the debugging that you need for this course and a lot of the debugging for 222. But there are other things you can do, right? You can set up watch points that say, hey, when a variable changes value, treat that like a breakpoint and come back. We can do things like change our layouts so that instead of debugging C code, we're debugging assembly language code. And we can say, let's step one instruction at a time. And now, you know, we're actually looking at the assembly language code that makes up our program. And we can print the values of registers and examine memory locations. And we can basically, you know, debug this at the hardware level. And this is a really useful and fun way to kind of dig into computer architecture and learn assembly language and things like that. And this is, you know, now like a good afternoon in Engineering 270, where you're just stepping through code one instruction at a time and trying to figure out what it does and so on. And here we're actually debugging the printf function, right? So this is the assembly language that makes up the C code that makes up printf. So we're not going to play with that in this course, but you know, it's an option. All right. That's probably all I need to say on GDB for now. We'll use this a lot. But that's all we need for now. The other comment I'll make is that also on Canvas, under the possibly useful videos, there's this short GDB tutorial video. This is short. I think it's like 20 minutes maybe. Oh, I got commercials. Yeah, so it's 20 minutes and it basically goes over everything that we've just gone over with a different use example and showing you how to debug a C program using GDB. If you're not sure how to do any of this, if some of what we said didn't make sense, strongly recommend looking at this video. It seems to do a pretty good overview of all of this. And the sooner you get good with GDB, the better. And you can definitely use it in PA2 as you're developing that code to help track down problems and such. All right. Good enough for now. So let's take a short break. Let's come back at 11:18. We'll take about a 3 or 4 minute break. Come back and we'll dig into some Linux stuff and explore that a little more. So I'll see you back in a few minutes. All right, welcome back. So, you're going to keep doing C for PA2, and that's kind of our last big C project for this course. And a big part of this course is, learning about tools and working in a Linux environment and getting better at using Linux to help us do our work. Because, the rest of the sequence is done in Linux. A lot of courses at university are done in Linux. And so we want to get as kind of proficient with Linux as possible. With a bare minimum understanding of Linux, you can still do the things you need to do, but they may take you a lot longer than if you learn some tricks and tools. And so big part of this course is going to be, learning to work in a Linux environment, learning some of the tools that are available and so on. And one of those tools is scripting. And so we're going to start talking about scripting today. And scripting is the idea of basically writing programs inside Bash. So remember, Bash is a program. Right now, you're looking at my Linux window, and there's a prompt and a cursor blinking. I'm sitting inside a program called Bash, which is executing. It started executing as soon as I created this terminal window. And if I use the command PS, which shows me processes on the system, I can see there's a process with this ID running the command bash. And that's the program that's actually running that I just typed PS into. And part of what it did was it created a new process to execute the command PS. And so bash is, among other things, a way to execute commands. It's a way I can type in something and bash will look for a file with that name. And if it finds it, it will execute it. So there's a file called date in a directory, and that's a program that tells me what the date is. But bash is also a programming environment. And so one thing we can do is we can create variables. So I can create a variable like x, and I can say x equals 5. And now I've saved 5 in this variable. And if I want to see what the value of a variable is, I can say echo. So echo, repeats whatever I tell it. It's just an echo chamber. Echo, this is fun, says this is fun. But if I echo a variable with a $sign in front of it, it says, show me the value of that variable. So if I echo $x, it gives me a 5.
What are the scope of these variables like? If we change something, if we changed X on the Linux server, would it change X for everyone else or just us?
So this is strictly within this bash session. And if I start a new bash session and I look at X, it's not defined, it's just an empty string. But inside here, X will be 5 and it'll always be 5 no matter what I do. And we know about pipes, I could echo $X and pipe that into cow, say, and my cow will tell me the value of X. But it's mostly a local variable in some sense. So echo is like a print statement. We can use it to print a message, but we can also use it to print the values of variables. And usually when we say echo, we want to put our statements inside double quotes. And we'll see why in a little bit. But I could say something like, X has the value $X. And it prints out X has the value 5. So to print the value of a variable, just put a $sign in front of it. Now, if I say y equals x, and I look at the value of y, it's x. Why? Because I said y equals x. These equal statements, these assignments are extremely literal. So it you know, says, oh, I should set y equal to x. Okay, that's the value of y. But if I say y equals $x, now y is equal to 5. Yeah, perfect. If I say y equals 1 plus 1, guess what? Y is 1 plus 1. So equal signs are ways we assign values to variables, and it's pretty much literal. So normally we say, you know, double quote something, but if we wanted to actually set y equal to the string $x, we can put that inside single quotes. And single quotes are just like double quotes, except they say, don't treat $sign as a special character. It's just a $sign. So if I say y equals single quote $x, and then I echo $y, it's equal to a $sign followed by an x. Sometimes we spend a lot of time in Bash playing around with quotation marks, but oftentimes it's just as straightforward. Put things in double quotes, put them in single quotes if you want to suppress the $sign. But we could also do something like this, echo double quote, the value of single quote $x is $x. Hope that didn't work. So we can do that to say the value of $x is, and then we can echo $x actually get a 5. All right, so this is a good time to mention that Bash is one of the pickiest languages you're ever going to work in. So for example, if I say x space equals space 12, it gets upset at me. If I say x equals space 12, it gets upset. If I say x space equals 12, it gets upset. It's got to be x followed by an equal sign followed by the thing you want to set it equal to. And extra spaces mean things to Bash. They usually mean things we don't want them to mean. So you got to be careful with syntax. And so this brings up, yeah, like Pythons on tabs, exactly. But even pickier, if that's possible. So this brings up something else. If you look on Canvas, there's a Bash how-to / summary of Bash ifs, loops, and arithmetic. All right, so here's the deal. I'm usually not dogmatic. I usually tell students, you know, if you can write your code in a way that makes sense to you, that's the way to do it. And for C, that's still what I believe. But Bash, because it is so picky with syntax, I'm going to insist in this course that you use one particular syntax for writing Bash. And that syntax is spelled out in this Bash how-to summary of Bash ifs, loops, and arithmetic statements. And all the Bash that I do for you in class, all the Bash that I write on the paper here and that I type in code will follow this guide. And here's the deal. When we write an if statement in Bash, we're going to say if space, 2 square brackets with no spaces between them, space, some condition, space, 2 square brackets with nothing in between them, new line, then new line, body of the if statement, new line, and the word fee. And every time I write an if statement, it's going to look like this. The deal is sometimes you can use single square brackets and it'll work. Sometimes you can use parentheses and it will work. And sometimes it won't. And if you write code for an assignment and you use single square brackets, maybe your code will work in that case. But if you don't understand when a single square bracket will work and when it won't, there's a danger that, you know, on the job or in a coding interview or something like that, you might write an if statement incorrectly. And the person's going to look at it and say, you know, well, that's not going to work. Or they might, you know, ask you, why did you use a single bracket instead of two? And if your best answer is, well, I tried different things and that was the one that seemed to work, you know, 2 years ago when I took a class, that's not a terribly comforting answer. So I'm going to stick to one set of syntax for if statements, for while loops, for assignment statements, for calculating arithmetic expressions. And I'm going to insist, just in this case, that when you do bash for this course, you do it exactly the same way. Now, you can choose, you know, how you're going to implement an algorithm, how you're going to put together if statements and loops and arithmetic and so on, based on, you know, your program that you're going to come up with. But when you're coming down to the syntax, right, if you're writing an if statement in bash, it's going to have to look exactly like this. And same with while loops and so on. And I'm never going to let you do for loops in bash because they break this syntax. And it's kind of a one size fits all kind of thing. Yeah. It works well for all the cases that we're going to encounter. And, you know, outside of the class, after the class, for code you're writing for yourself, if you want to learn other ways to do things, if you want to use for loops and so on, go wild, right? Because there's a whole lot more to bash. And there's reasons why sometimes people will use parentheses instead of brackets. But we're not going to go into those. And so I'm going to expect you not to use those, basically. All right, so let's accept that bash is picky. And so we can do assignment statements like this, and we can echo to print out values of things like this. And so let's write a script. And so a script is basically a program that consists of a bunch of bash statements, one after another. And so where am I here? So let's make a script called hello. And this script's going to be pretty straightforward. It's going to say echo, who are you? And I'm just going to say name equals Nick. And it's going to say hello $name. Well, let me get rid of this. So we can make comments by putting number signs in the beginning of a statement or after some part of a statement. So number sign is like a / and C, make something a comment. So let's just start with a really simple program. We'll just say name is equal to Nick, and we'll say hello, and we'll use $name. So this is a program that'll say hi to me. And it's in a file called hello. So to execute it, all I have to do is say hello. But by default, it's not going to let me do that. The reason being that if you take any old file, like, you know, the readmes for the ODPs, and you type their name, you don't want to execute the stuff inside that file as if it was a bunch of commands. So by default, files are not executable. So if I do an ls-l, I see this information in the beginning. These are called the permission bits. And so every file has 3 sets of permission bits associated with it. And they look like this. So these are the bits for whoever owns the file. These are the bits for people who are in the same group as the person who owns the file. And these are the bits for everyone else. So when I do an ls-l, this first name, that's the owner of the file. And this is the name of the group to which the file is associated. We don't have to worry about groups too much in here. We're mainly interested in owner. So the file is owned by Nick, which means these bits, RW- control what Nick can do to this file. So if we look on the Linux server, here's a file called big. It's owned by Nick. And so these bits RW- say what Nick can do to this file. The group associated with this file is a group called faculty. And so these next 3 bits say what people in the faculty group can do to this file. And then these last 3 bits say what everybody else can do to the file. So we got a total of 9 bits. So here's message of the day -fake. These 3 bits RWX, that's what Nick can do. R-X, that's what people in the faculty group can do. And R-X, that's what everybody else in the world can do. And the meaning of these bits is R means that you can read the file, you can look at it. W means you can write or modify the contents of the file. And X means you can execute the file. And so my problem here is that this hello, I don't have execute permission. So I'd like to get an X in here. So I want the permission on this to be something like RWX. That means that I can read, write, and execute the file. And maybe for other people in my group, I'll let them read the file and execute it, but I don't want other people to modify it. And for the rest of the world, yeah, I'm okay if they read it, and if they execute it, I don't want them to modify it. So maybe I want to set the permission on the file to look like this: RWX, R-X, R-X, instead of this. All right, so we use a command called change mode. And I can say change mod, and I can put in a bit pattern that specifies this, and then I have a file name. Okay, so how do I get the bits? Take the pattern that you want. If you want to grant permission, that's a 1. If you want to deny permission, that's a 0. So 1 means permission. 0 means no permission. And then write this in octal. So as a 3-digit octal number, this is a 5, this is a 5, this is a 7. That's what goes right there. That's a goofy little procedure, but it's really not as bad as it seems, because usually we're using 1 of 2 bit patterns. So for me, I'm just going to say change mode 755 hello. And now if I look at hello, I've got read, write, execute, and everybody else has just read and execute. All right, and yeah, this first character says what kind of file it is. So these things are directories if they have a D in the beginning. A dash means it's just a plain old file. And there's other things. If there's a C, it's actually some sort of device for doing input or output. And this is a device that's character based, meaning it's stuff that works pretty well for humans. If there's a B in the beginning, it's a binary character device. If there's an L, it's what's called a symbolic link, and we'll talk about links another day. But it's a way to set up one file that's actually an abbreviation to another, so it's a shortcut if you're in Windows. But it's just a link. All right, so I've made hello executable, and I should be able to execute it. So now if I say hello, it actually runs the contents of that file as if they were a bunch of commands. Remember, hello had two statements: set name equal to Nick, and then echo hello $name. So now when I say hello, it says hello, Nick. So there's our first script. All right, let's modify this. So, you know, this will always say hello, Nick, but that's not very friendly for other people. So we can ask the user, who are you? And instead of saying name equals Nick, we can do the following. We can say read name. So the read is a statement which says, let user type something. And then we save what they typed, in this case, into the variable name. So now if I run this, and it's still runnable, permission bits don't change on their own. They're set when the file's created. I already changed them to make this executable. It's going to be executable for the rest of eternity. So now when I say hello, it says, who are you? And I can say, my name is, you know, Zog. And it'll say, hello, Zog. So that's our second script. All right, good so far. All right, let's add an if statement. So I said the general syntax for an if statement is like this: if bracket bracket some condition bracket bracket then body of the if statement and a fee. And this how to on Canvas spells that out. So if bracket bracket condition, then things to do if the condition's true, and then a fee. And the only question is, what are these conditions? And so examples of conditions, if we want to compare two strings, two collections of characters to each other, we can do it like this. So we put our strings inside double quotes, and we could have, you know, a set of characters, or we could have something like, you know, $sign followed by the name of a variable, and that'll get replaced by the value of the variable. So we'll say, who are you? And we'll read the name. See if the user is actually Nick. So we're going to use an if statement. If bracket bracket quote $name unquote equals quote Nick, close brackets, then, and we can say something like, you know, hello, Nick, welcome home. And we'll just exit. But if the name is not equal to Nick, this is not Nick. We'll say unauthorized access detected. All right, so we say hello, it says, who are you? If I say Nick, it says, hello, Nick, welcome home. Now, if Zog tries to infiltrate my script, who are you, Zog? It'll say unauthorized access detected. So this is, you know, a more sophisticated script, not terribly sophisticated, but you know, this shows us how to do an if statement. And so our if statements can compare strings. We could say exclamation mark equals to see if something's not equal. So for strings, this checks to see if things are equal, this checks to see if things are not equal. But we can also compare numbers. And to compare a number, we use these extra switches like -LT to see if something is less than, -NE to see if something is not equal, -EQ to see if something is equal. And this will actually treat both sides of this condition as a number. And so it'll do numeric comparisons. And so in Windows, yeah, these are old batch files. So like a .bat file would have a bunch of Windows commands. And if you type the name of the batch file, then it would execute those commands. So these are basically like batch scripts. All right, well, we can do some looping. So let's yell at the user a bunch of times in a row. So let's display a nasty message 10 times. So let's set I equal to 0. This is our loop counter. And then our while statements look like while bracket bracket condition bracket bracket do statements we want to do, and then a done statement. And so we could say while bracket bracket $i is less than 10 do, and we're going to echo this, and then we want to say I equals I plus 1 and done. And this is almost going to work. So Nick is still fine. Zog will get yelled at, and then our script will crash. And we got some cryptic error about expression recursion level exceeded and so on and so forth. When I said I equals I plus 1. So this is not going to do what we think it's going to do. Right? Remember, if I said I equal to 0, and then I said I equal to I plus 1, and I look at the value of I, it's I plus sign 1. So we want to actually do arithmetic. We want to take the value of I, add 1 to it, and store it back in I. And there's a way to do that. And that's saying $, and then double parentheses and some expression. And this will evaluate this expression in the way that we would expect a programming language to evaluate an expression. So I'm going to do the following. Instead of I equals I plus 1, I'm going to say I equals $paren $, I plus 1. So this actually evaluates an expression. And so this should take the current value of I, which is 0, add 1 to it, set I equal to 1. So with bash, you know, we can always test these things on the command line. I can say I equals 0. What's the value of I? It's a 0. If I said I equal to $paren $, I plus 1, plus 1. And then I look at the value of I, it's a 1. If I said I equal to $paren again, I is equal to 2. So this should increment I, go back to the top of the loop. If it's less than 10, it should yell again. And so this should print out this message 10 times. We'll say hello, Zog will try to come in, and there's our 10 messages. All right, at some level, this is all you need to be able to write bash scripts. You need to be able to execute sequential statements, do conditional statements, and do looping. And if you can do those, you can do pretty much anything. All right, so how does this work? This works because the way that bash is set up, if I just type, something, it will look for a file that's executable that has that name. And if it finds it, it will execute it. Well, there's no file with this name, so I get a message saying command not found. But if I say hello, it searches. And remember, it searches in these directories in this order. And, so now we know path is just a variable in bash. And when I say echo $path, I'm seeing the value of that variable. These are the directories where it searches for a command. Dot is my current directory, so it's searching in my current directory for a file called hello. And since it finds it, it executes it. But how does it execute it? Because this does not contain assembly language code. This does not contain binary code. It contains, bash commands. Well, when bash is asked to execute a file that contains plain text like this, it treats the contents as if it were a bunch of bash commands. But there are other shells available. There's a shell called CSH, which is like bash, but it's a totally different shell. And if I run this file from this shell, CSH, the Seashell, it doesn't work. It doesn't work because Seashell does not understand these kinds of statements. Writing a script for Seashell is different from writing a script for the Bourne shell, for bash. So I write this script and it works beautifully as long as I'm running bash, but if I happen to be someone who's using Seashell instead of bash, that script doesn't work anymore. So here's what we can do. We know that we can use a number sign to make a comment, right? But there's a special trick that all of these shells understand. And the special trick is if the very first statement in your file is a number sign followed by an exclamation mark, it doesn't just treat it as a comment. It expects this to be followed by the name of a program, such as /bin/bash, and it will use that program to execute the contents of this file. So if I say hello and Zog comes in, right, that works fine. If I'm running Seashell and I say hello and Zog comes in, it still works. Because that first statement, which is called a shebang, says, hey, if somebody tries to run this, whatever shell you're using, I don't care. Use bash to execute these statements. That makes sense? So if we're writing a bash script, we're always going to make this the first line, and it's got to be the very first line. If it's the second line, it's not a shebang anymore. And it's not going to work. So the very first line of your script has to be this number sign exclamation mark followed by the path to bash, which for us is /bin/bash. All right, good. Let's see, 2022 1013 R02D scripts.
So is the rest of the class going to be in this language?
Largely, yes. So, PA2 is the last C program. So the rest of the programming that we do is going to be in Bash. We may come back and talk more about some C along the way. And, certainly C will be on the midterm. So we'll review that and we'll talk about it after the midterm and so on. So we're not totally done talking about C, and we've still got another week and a day for PA2. So, but yeah, for programming, we're going to shift over to doing Bash programming.
Are the assignments in Bash going to be like like in depth? Should I expect to be doing something like PA1 or 2 in Bash?
So PA3 is going to be something like PA1. I'm not going to do the stick game again, but it'll be something on that order. And then PA4 will be a more ambitious Bash script. And then PA5 will be a group project, and we'll be playing with some GUIs for PA5.
Okay, cool.
And we will get there. It's a different language. It has this quirky syntax. It has all of these, peculiarities about if I don't put a space there, weird things might happen. The universe might implode or something. But it's just another programming language. And once you get past the kind of quirks of it, it's actually one of the most powerful languages you can work in, because it gives you access to everything that you can do in Linux. I can run, any Linux command from here. I can grab the output of it. I can manipulate it. And there are so many amazing tools in Linux, awk and sed and grep and all of these things. And once we're better versed in using these different fundamental tools, being able to put them together in a sequence becomes just an amazingly powerful tool. Yeah, exactly. Just another programming language that happens to have the power to make the universe implode if you miss a space. That's a good synopsis of Bash. Thank you. So yeah, and I learned Bash or Bourne Shell, decades ago, and never really did much with it until COVID. And when COVID hit, and at the end of winter 2020, we started moving things online, and then spring quarter was entirely online. I found that I was doing, dozens, maybe closer to 100 things to get my class ready to go in the morning. I would have to, open up Zoom, and I'd have to open up certain windows in Zoom and start a document camera and set the aspect ratio of it and put it in a particular position and set it so that it's always on top. And then I had to put up a little progress bar and a recording, and I'd open up my Zoom camera and I'd make that persistent on desktops. And I'd do all of this stuff, right? And it was, tons of commands I had to write. And I started writing scripts to do these things. And that's when I fell in love with scripting. And now, I can just say cam setup, and it'll do all those things I just described. Create a document camera, put a camera up here, make them, sticky or not sticky, put them in the right place, and so on and so forth. And so since that happened, I've really embraced scripting, and it's made things so much quicker across the board. And I spend a lot of time, sitting behind a computer doing stuff. So this is all, automation, basically. All right, so two other things I want to mention briefly. So the first one, so I just pushed this over to the server into the shared code area. So there's a code with a directory with today's date, and you can find this code there. If I echo, an asterisk, I get an asterisk. But something really weird happens if I just say echo asterisk without quotation marks on it. It says hello. And that might and probably should seem kind of strange. And if I'm in my login directory and I echo asterisk, it says a whole bunch of stuff. And all this stuff that it's saying to me when I say echo asterisk is actually the list of files that I have in this directory. So what's going on here? We know, for example, that you know, I've got some code in here, right? So, well, let me just do this. All right, so I got some files in here, A.C, B.C, and main.c. So you can use wildcards to do things like, you know, if I say ls star.c, it'll just show me my .c files. If I say ls-l star.c, it'll do a long listing on my .c files. If I say vi star.c, it'll show me my first file. And if I say :n for next, it'll go to the second, and :n will go to the next. And then :n will say there's no more files. And if I say like gcc-c star.c, it will try to compile each of my C files, A.c, B.c, and main.c. So we can use these wildcards in lots of different commands. But the thing about bash is the thing that actually processes these wildcards. So if I say echo star.c, I get a list of my .c files. So here's the deal. With bash, when I type a command, before that command is executed, if I say like command star.c, before command is run, bash will look in my current directory and find which files match this wildcard and replace this with a list of those files. And then it runs commands with all of these things on the command line. So my program does not have to itself figure out how to deal with these asterisks. It just needs to process multiple things on the command line. So when I say cat star.c, the cat program is not looking at this star. The cat program is seeing 3 command line arguments, which are A.c, B.c, and main.c. And cat just reads each of these command line arguments, opens the file, prints its contents, closes it, goes on to the next file. So wildcarding is handled by bash, which means that wildcards can always be used with whatever programs we're writing. And this works for C programs. This will also work for shell scripts. And the 2 main wildcards that we can use a star to match any sequence of characters, and we can use question mark to match a single character. So if I want to see all my C files that have a single letter in their name, I could say list question mark.c, and that'll just show me A and B. All right, good. Yeah, so it's very much like a regular expression, but not as powerful. And we'll do regexes separately. But this is just a basic wildcard subs. All right, so yeah, go ahead.
Yeah, quick question. I'm assuming that you're teaching us all of this in Linux because when we go to work for a company in the future, whatever the heck you want to call it, you would be able to easily set up a Linux environment unlike any others, and then just simply create the code that you would use and then just export that to the right software.
I don't know if I parsed all of that correctly. but basically we're learning this because you're going to be working in a Linux environment a lot of the time, right? All the courses at Clark, the majority of CS courses at WSU, and very likely, you know, in courses in a workplace situation. And so being able to write scripts in something like Bash, you know, is in some ways as useful as being able to write, you know, C programs in C. It's going to let you streamline your work. It's going to sometimes, you know, be a better way to perform some higher level function. So for example, when I grade assignments, right, I go through the assignments, and as I note things like, you know, this does not work correctly in this particular input case, or you're missing a comment block in the beginning, or things like that, right? Rather than write those comments, you know, 30 or 40 times, I just have a little short abbreviation I use for those. And I make a file with your name and those, you know, mnemonics for the comments. And then I have a script that I can run through that will take those mnemonics, turn them into actual comments, calculate the point deductions for them, subtract it from 100, figure out what your grade for the assignment should be, along with all those comments, put that all on a clipboard. And so I just run that one command, and then I can paste that into the comment block and copy the grade into your grade block. And it makes grading, you know, about 10 times faster as far as the mechanics of typing in comments again and again, and making sure that I'm doing the same, you know, point values for certain things for each student, and so on and so forth. And that's just a Bash script. And so it's part of, let's see, so yeah, this looks good. Most programs aren't Bash scripts, but scripts can be a tool for devs like Makefiles, I think. Yeah, so this is true. But a lot of the tools that you're going to use are really just scripts. When you download commercial software, a lot of the times, the main thing that you run is a big script. And the script, among other things, can run other programs, but can do it in a controlled way that responds to, you know, user input or aspects of your environment and so on. So it's all just tool building, basically.
Okay, so this would be like, we could put together a file which would automatically submit our homework to Git.
Yeah. So you could make a command like go, right? And go would automatically do a git add, git commit, git push.
The main thing I'm thinking would be helpful is a command to put it to generate at least the basics of a header comment, so that you don't have to do the date like modified and created and your name, because you know.
Yeah. Are you talking about for Git or for like comment blocks in the beginning of code?
Beginning of code.
Yeah, so I mean, you could make a function called, you know, add header that would, you know, automatically add a line with your name and the class and the current date and, you know, some boilerplate information. And you could say, you know, add header space index.c, and it would just go ahead and tack that into the beginning. So there's a zillion things we can do with scripts. And like I say, even though I knew how to script for a long time, I didn't really start using it until I got to a point where I was being overwhelmed with how many things I had to do once I logged in before I was ready to get on to something else like teaching, right? And so it was automating those. But during the course of project development, you'll encounter these situations again and again. I have to, you know, log into this machine and go into this directory and do, you know, a git pull. And then I have to, you know, change this window to use blue text instead of green, because this is where I do my compiles and whatever, right? You can automate all of that. All right, we're a little bit past time, so I'm going to take off here. On Tuesday, I will give you the last bit of the quotation story. We've got double quotes and single quotes. We can also use back quotes, and back quotes are the key to unlocking the full power of scripts. So we'll start with that on Tuesday, and that will open up a lot of doors for us. All right, I got office hours tomorrow morning at 5. I will see, at 7:30. I'll see you there, or I'll see you next week. Hope everyone has a good weekend, and I will catch you next time.
Thank you. Have a good weekend.
Thanks, you too.
Have a good one.
Thanks.
Thank you.